our new seminar series, the RRI Quantum Science and Technology Seminar, or webinar as it is called. This quantum science and technology is actually, I mean, from what we see even in India.
You need to unmute yourself.
Somebody is muting me. So, no, I didn't do that. So, Abhishek Shanchari Surya, please don't mute me. They are my co-hosts. They are my students. So, I am not responsible for this. So, I will start once more. But Chao-Yang, you tell me if I'm muted again, so we can help each other. So, I will start once more then, because I don't know when it began. But of course, again, I'm very happy to welcome you all to our new seminar series, the RRI Quantum Science and Technology Seminar Series, or the webinar series as it stands. This field is poised to play a very revolutionary role in the foreseeable future, and with tremendous interest in the developments in this field that we see in India and abroad, globally, we feel that it is important to have a forum where one can have interesting and exceptional work in this domain discussed and debated upon. I mean, Chao-Yang, that is one of the things we would like to debate on the work as well. And so in this seminar series, we hope to have in-depth technical and scientific seminars on various aspects of quantum science and technology. Well, without further...
Muted again.
Yeah, thanks. I don't know what is the Zoom thing. Yeah. So, but then, of course, without further ado, I would like to, go on to introduce our inaugural speaker, Professor Chao-Yang Lu. Chao-Yang Lu was born in 1982. Chao-Yang, you're too young for all these accomplishments that I will now read out. So, but then that is what it is. He was born in Yizhang in China, and he obtained his bachelor's degree from the University of Science and Technology, China in 2004, and PhD in physics from the Cavendish Lab, University of Cambridge in 2011. He is currently a professor of physics at USTC. His current research interest includes quantum computation, solid-state quantum photonics, multipartite entanglement, quantum teleportation, superconducting circuits, and atomic arrays. His work on quantum teleportation was selected by Physics World as Breakthrough of the Year 2015. His work on single photon sources and optical quantum computing was selected by Optical Society of America as one of Optics of 2016, Optics in 2017, and Optics in 2019. I wonder what happened to 2018. While I was reading this, came to my mind. He has been awarded as Fellow of Churchill College in 2011, Hong Kong Kyushi Outstanding Young Scholars 2014, National Science Fund for Distinguished Young Scholars 2015, Nature's Top 10 Science Star of China 2016, OSA Fellow 2017, Fresnel Prize from the European Physical Society 2017, AAAS Newcomb Cleveland Prize 2018, Huang Kun Prize from Chinese Physical Society 2019, IUPAP ICO Young Scientist Prize in Optics 2019, the OSA Adolph Long Medal 2020, and Rolf Landor and Charles H. Bennett Award in Quantum Computing 2021, and some others. Okay, so he's the chair of Quantum 2020 and has served as an editorial board member in international journals such as Quantum Science and Technology, Photonics, Advanced Quantum Technology, Science Bulletin, and iScience. I could go on, but I think it would be more interesting to actually hear about the wonderful science that Chao-Yang will talk to us today about. He is going to tell us about their group's very interesting journey on quantum supremacy and beyond. So with that, I present to you Chao-Yang Lu.
Thank you very much, and for the very kind introduction and also for the invitation. So good afternoon, friends from India, and good morning for the friends from Europe. I think this time is not very convenient for United States, so I assume there's no one from the United States. So Thanks for the very nice opportunity to present our recent work on quantum light source and quantum computational advantage. As we know, among many different types of qubits, photons have certain advantages. They are fast flying, so very well suited for long distance quantum communications and can be used to link distant quantum computers. The quantum information encoded in photons are very robust. Actually, people say that those from the Big Bang, they still preserve their polarization. And, the information in photon can be controlled with high precision, thanks to the sophisticated photonic technologies. And for the other advantages, you can read the recent point by Christian Woodbrook. So using photons, quantum communications have gone long distances. In China, assisted by major satellite, quantum key distribution, entanglement distribution, and quantum teleportation have all achieved over a distance of 1,000 kilometers. In 2017, actually, even intercontinental quantum-safe video conference between Vienna and Beijing has been reported uses a satellite as a trust relay. So now a natural question is that whether we can also use the photons to perform quantum computing. So the advantage of photon having very weak interaction, I just mentioned, here now becomes a disadvantage because quantum computing crucially relies on controlled interaction between qubits. But it's very well known that the optical nonlinearity at a single photon level is extremely weak. Interestingly, some effective interaction can still happen between single photons if they are quantum mechanically indistinguishable, which means there's no way, even in principle, to tell the difference between two photons. In this case, if we combine two photons on a 50-50 beam splitter, they will always exit to the same output, but never one in each output. This is due to, you can see there's 4 probability amplitude, and if the two photons are actually identical, these 2 probability amplitude will cancel out. And this is a pure quantum interference effect. It's actually interesting to recall the history of linear optical quantum computing. So because, although as I talk about, identical photons can interfere, but based on the interference effect, the photon logic gate cannot succeed successfully. There's only a small probability. So 20 years ago, 3 scientists, Neil, Laughlin, and Melbourne, they started, with the intention to prove a no-go theorem for scalable linear optical quantum computing. Interestingly, they end up in proving that it's actually possible. And there were further improvement that reduced overhead from about 100,000 single photons for one near deterministic signal gate to about less than 100. And also, in recent years, there are some quantum startup already launched using photons to perform quantum computing. However, clearly, if we wish to build a fault-tolerant quantum computer based on photons, for example, to factorize a 300-digit number, then there's a huge gap, more than 6 orders of magnitude, I should say, between the photon numbers that are needed for running a non-trivial Shor's algorithm and what the current laboratories can control and can create and can control. So a realistic roadmap for quantum computing would be in Chinese saying, we call it laying eggs along the way. So because the fault-tolerant quantum computing is still a very distant goal, to ensure that the quantum computing field is healthy and can continuously produce meaningful results, we also should have near-term plans and mid-term plans. So the near-term plan was to demonstrate quantum computation advantage, which means that a quantum device can be built and it can solve a well-defined computational problem, which is not necessarily useful, but with speed, that is overwhelmingly faster than any classical computer. And based on that, a next step will be to build practical quantum simulators. So
Chao-Yang,
showing,
Chao-Yang,
hi,
just yeah, hi. And also to ensure that I can assure you that we are still there. Sometimes Zoom seminars are interesting. I just wanted to give a quick introduction. Is it okay for you to take questions during the seminar? Because then it's a little more interactive. Otherwise, we can have everything in the end. What is your preference? So we'll go.
maybe everything is end. So
You
first
prefer
you may
everything.
collect the questions, and in the end, I can go back to where the question is. So
Okay, so what we will
that
then
might be
do
more
for
convenient.
the audience here, if you have any questions which come up as he's speaking, please do share them in the chat window if it is reference to some specific time of the talk. And then, of course, in the end, we will take them up from there, or we will have people actually speak with unmuting depending on the number. Yeah. So that is how we will do it then, Chaoyan. Yeah. Okay. Thanks.
Yeah, I can also look up the questions in the chat window, and I can just answer one by one. So as I said, in the quantum computation advantage, to show the quantum speedup in an actual experiment will not only enhance our confidence to build practical quantum computers, the long-term goal, but in itself is also of fundamentally important, because it can be thought of as a computational analog of Bell experiment. So just like the Bell experiments were designed to refute Einstein's local hidden variable model and to establish the experimental evidence, the quantum entanglement as a valuable resource with stronger than classical correlation. Quantum supremacy experiment will refute the old extended Church-Turing thesis and prove the potential of fast than classical computation using quantum mechanics. Among the candidate algorithms to demonstrate quantum supremacy, boson sampling and random circular sampling are particularly well suited for experimental implementations, which require only 50 to 100 reasonably high quality physical qubits. And if we compare the quantum sampling algorithms to Shor's algorithm, it's interesting to note that the sampling algorithms are much easier to realize because both the number and the quality of the physical qubits, but also from the theoretic complexity theoretical point of view, they actually have a stronger evidence because these problems are related to sharp p-hat problems in the complexity theory. So Google and the USSB have focused on random circular sampling using super-diagonal qubits in the past 6 years or so. And by quantum engineering of increasing large number of qubits and with high quality, they were able to build a 53 qubit Sycamore system and obtain 1 million sample, which they estimate would take about 10,000 years for a supercomputer. And the next day after they published their paper, however, IBM argued that the 10,000 years can be shortened to about 3 days. This is because the 53 qubit is still within today's storage capability. And using IBM's algorithm, if we change the task to generate more samples, for example, 10 billion samples, then actually, the Google experiment will show no quantum advantage. Actually, the classical will be 10 times faster. So I will steal one slide from a workshop just a few days ago by Professor Umesh Vazilona. So he also pointed out that quantum supremacy is not a single shot achievement, but will have to be refined over time to eliminate loopholes, because the classical computer scientists are very clever and they will come up with better and better classical algorithms. So now let me return to the focus of this talk. So the quantum algorithm we are interested in is boson sampling using photons. And in this algorithm, there will be an array of quantum light source is sent into a large interferometer, and its output distribution are sampled. To estimate the probability of a certain output distribution using a classical computer, we can calculate the corresponding submatrix permanent. And the permanent is a notoriously hard computational problem that is believed in the Sharp-P-hard class. It is a very remarkable theoretical result is in 2013 by Scott Allison and Alex Akipov. They prove that precise and even approximate or noisy classical simulation of boson sampling would imply a collapse of the polynomial hierarchy. So now let's talk about the experiments. It seems fair to say that the earliest experiment for boson sampling, using just 2 photons, have already performed in 1987 in the famous Honger-Mandel interference. Later on in 2013, 4 independent groups demonstrated the case with 3 or for some special case 4 photons. It was argued by Scott Allison and Akipov that the eventual goal would be to demonstrate boson sampling with 20 to 30 photons, because this is the region to outperform. This was the region they believe to outperform its fastest classical simulation. And unfortunately, the most significant challenge was the lack of perfect single photon source. So what is a perfect single photon source? Ideally, a perfect single photon source should simultaneously fulfill the following checklist. So the generation, collection, and the detection of single photons should have high efficiency, should have near unity efficiency. The emission should have near 0 multi-photon probability, and the photons should be identical to each other in all degree of freedoms, so that there's no way, even in principle, to distinguish them. So this is the part of the quantum light source. In addition to the source, there are also circuit and the detection. So the optical network should have full connectivity, which means any input photon can go to any channel in the output. And the matrix should be hard random, so that the computational problem is hard, because for any matrix with some structure, you can find some easy way to, you can find some shortcut. And the photons inside the network should have near perfect wave packet overlap and phase stability, and high near unity transmission rate, so that photons are not lost. And in the output, we should have high efficiency detectors with low die counts. So fairly constantly in quantum computing experiments, the biggest challenge is to get many of the quantum computing components, which sometimes can be contradictory, to work together. as I will show later, for photons, usually there's a trade-off between the efficiency and indistinguishability. In other quantum computing systems, you can see, they can be trade-off between the conjugability and the coherence. Usually, a system which is more, very easy to control, they will have usually have a bad coherence. So in 2013, when we started to seriously consider experimental implementation of larger scale boson sampling, we collect the best figure of merit of the single photon source, optical circuit, and the detection, and we put all the three together. The best figure of merit in all the three, and together we estimate that a 50 photon coincidence count rate will be 10 to the power of minus 150, which is extremely low. So what are the problems? Why is the count rate is so low? So first we think about, first we consider the quantum light source, and we start from the SPDC. SPDC has been the most used workhorse for multi-photon experiments. It's well known that the SPDC has an intrinsic problem, that the emission is probabilistic. It doesn't give you a photon pair every time. And even worse, it has some multi-photon contamination, which means for p square probability, it will have double pair. It is, however, not as well known that actually after 2 decades of development, SPDC has less obvious problems in the collection efficiency and in the trade-off between efficiency and indistinguishability. So, for example, if we usually collect entangled photons from the intersections of the two down conversion rings, the O ring and the E ring. The intersections are obviously, they are not in a very good Gaussian shape and cannot perfectly couple into a single mode fiber. So in 2016, we engineered SPDC so that the two rings are converged into two separate circular beams with Gaussian shape, which are more favorable for collecting into a single mode fiber. A remaining problem in the 10 photon entanglement work is that, as we see from this left figure, there's some still unwanted spectral correlation, which can be seen from the tilted joint spectral correlation. So in this case, we will have to use narrowband filtering to sacrifice efficiency. Otherwise, the unwanted entanglement in correlation in the wavelength or in frequency will provide which way information of the of photons polarization. So we adjust the phase matching condition of the crystal so that the spectral correlation becomes circular. So in this one, there will be no frequency correlation. And this creates a SPDC source with simultaneously 97% Heralding efficiency and 96% indistinguishability, which means with this source, so previously we always need a narrowband filtering to perform the multi-photon experiments, but with this new source, we do not need any narrowband filtering anymore. Now let's switch to a quantum dot, which similarly also suffer from similar quality and quantity problems and also the trade-off. So the indistinguishability of the single photons from quantum dot strongly relies on the way you optically excite the quantum dot. And previously, the predominantly used method of non-resonant excitation will first generate free electron and holes in the above band, which are then incoherently relaxed into the lowest level to emit a single photon. So one problem is from the relaxation time, which is uncontrolled. And this time jitter can become comparable to the coherence time of the single photons. And the second problem is that the near saturation driving laser power is usually tens of microwatts, which cause electric field because excitation is not very efficient. So it will cause many free electron and holes, and there will be electrical field fluctuation around the quantum dot, which broaden its line width. So these two problems are not technical, but they are fundamental and limit the two-photon interference visibility from the best record before, which was about 10 years ago in Stanford, to below 60%. To solve this problem, we developed pulsed resonant excitation, which directly drive the two-level system, so avoid any time jitter. We just take the solid state system, as a two-level system. And also, as you can see, that the pi pulse power is only a few nanowatts, which is 4 orders of magnitude lower than which I just mentioned before, tens of microwatts. So it will greatly reduce the electrical field fluctuation. As expected, then we can increase the photon indistinguishability to be around 99.5%. So as we see that, the use of resonant excitation has enabled both deterministic generation, evident from the pi pulse, so the Rabi oscillation, and also the high indistinguishability. The next problem is the photon collection. The photon collection in the solid state community is usually complicated because the quantum dot is embedded inside high reflective index material, and the emission of a two-level system is a dipole profile into 4 pi solid state angle. So using a bulk material, there will be only 17-degree, total internal reflection angle that can escape from the gallium arsenide, which corresponds to 1 to 2% of the overall extraction efficiency. So a straightforward idea is to have some cavity around the quantum dot. So to make the emission predominantly directional, we couple the emitter in a micropillar cavity, which has a diameter of 2 microns and a Q factor of about 7 to 8,000. Inside this microcavity, the emitter lifetime is then shortened from about 700 picoseconds of resonance to about 80 picosecond on resonance, with a Poisson factor of about 10. And you can see the numerical simulation. Both the laser and the single photon light field is strongly confined inside the pillow, and the emission is highly directional, and the far field pattern is near to Gaussian. So we can get the new Rabi oscillation data, and the pi pulse. The count is more than so our first data is about 9 million single photon counts per second, which we can calculate the extraction efficiency increased from 1% from the bulk structure to about 66%. And meanwhile, actually, the Poisson enhancement is also very favorable to increase the photon indistinguishability at a longer time scale, as you can see from this fundamental interference data. This is very encouraging. We get very high counts and also high quality. But this is not the end of the story. Getting high extraction efficiency is not enough. We need high system efficiency. And the use of resonant excitation actually cause additional problem, which makes the photon quality almost perfect, but it came with a price. So as I said, the laser, resonant meaning, the laser is exactly the same wavelength as the single photons. And then, the suppression of the laser background, which is, much, much higher than single photon signal, is much more complicated. So we usually use a polarizer to suppress the laser background. And if we work with a single electron quant dot, there are actually two degenerate transitions with random left or right circular polarization. So we use a linear polarized light for excitation and a cross-linear polarizer to get rid of the laser scattering. The use of polarization filtering, which almost, we can suppress the laser background by a factor of 10 to the power of 7 to 1. But also, meanwhile, it will cause efficiency loss of at least 50%. So this is a more tricky problem. It is not as straightforward as just use a microcavity to enhance the emitter. So we designed a new protocol that solves the two problems I just mentioned before. Two random transitions and the cross polarization filtering. So we designed a new protocol to solve the two problems simultaneously. And instead of using a symmetric cavity, we employ elliptical micropillar, which split the cavity mode into two non-degenerate linearly polarized modes. We put our quantum dot emitter on resonance with one of the cavity mode, say the H, which is red. So the pulsar enhancement is polarization selective. Most of the generated single photons will be funneled into this H polarization. This is not enough. We further design orthogonal excitation collection protocol. That is, we will excite with vertical with V and collect with H. So the trick is that the other cavity mode, the V cavity mode, which is separated from the H mode, but it should not be separated too far away. We will design it to have some small overlap, which will allow excitation using the V laser. So using this scheme, we fabricate the elliptical micropillar sample, which you can see from the left figure. And using the protocol, we generate polarized single photons. And as you can see from the middle figure, the degree of the polarization is more than 93%. So most of the photons generated are singly polarized. So at this point, we can see we can say that at least in principle, we now have a near perfect single photon source that simultaneously fulfill the high efficiency, purity, and indistinguishability. Recently, the idea of polarized microcavity was extended to other cavity designs, such as open cavity, which was just published this month by Richard Warburton's group in Basel. So here, there's the bad tunability, and the count goes up to 40 million per second with a record high system efficiency of 50%. And further optimization is possible, that we can increase the system efficiency possibly at 80% in the near future. And at this point, there will be a transition from science to engineering. We will have to make every step precise and stable, from the sample growth to fabrication, and all the way to have a perfect single photon source. So, but the problem is the eventual successful rate will be, it will be low. So having optimized single photon source, we can use optical switch to separate the single photon stream in only one spatial mode to many spatial mode. and it will be then equivalent to multiple independent single photon source. So this way we can just use one optimized sample and one correct set and avoid the complication of inhomogeneity of different quantum dots. So based on the single photon source we developed, we started from small scale test of boson sampling with just 5 photons in the year of 2017. And 2 years later, we scaled up to 20 photons and 60 mode 3-dimensional interferometer, which generates out-state space dimension up to 10 to the power of 14. And the pi pulse photon counts here, which we developed in 2018, was more than 15 million counts per second, which also we recently demonstrated some intensity squeezing. So looking back at the history of quantum dot-based single photon source, we are happy to see that after 20 years development, now we can control up to 20 photons. And as I said earlier, that we are in a transition from science to engineering stage, and we will optimize the system efficiency further. Currently, we have seen more than 35 million single photon counts per second, which will support our next boson sampling experiment with 30 photons. Originally, we thought that the 20 to 30 photons should be sufficient because as estimated by the theoretical papers. However, in 2017, there's a major improvement of the classical simulation or the classical sampling algorithm, which raised the bar to 50 photons. So going beyond 50 will demand the single photon system efficiency from generation, collection to detection altogether to be above 90%, which I'm sure that one day we will be there, but now is still a significant engineering challenge. So let's go back and look closer at the two different emitters. For the SPDC, we can see that if we can just forget about its Gaussian nature, then having simultaneously 99% indistinguishability and 90% efficiency is what we already getting very close in the 20 photon entanglement work. So I said, if we can just forget about the Gaussian nature, which means the probabilistic generation and the multi-photon contamination in SPDC, it has been a long-standing headache. As we see that if we increase the single pair generation probability, then it will reduce both the purity, the G2, and also the wave packet overlap of the SPDC photons. So very interestingly, a scheme called Gaussian boson sampling came as a rescue by these authors. So before I explain the working principle of the GPS, let's look at the original boson sampling again. It should be fair to say to summarize that that the quantum mechanical process is all about the sum of all possible probability amplitude. In the original boson sampling, the complexity mainly lies in the superposition of many possible paths that can lead to a certain multi-photon coincidence. For example, from input 1, 2, 3, 4 to output 1, 3, 4, 7, there are actually more than 20,000 possible paths which will add up together. So in Gaussian boson sampling, instead of using single photons as input, which was expensive, as I just explained. So the GPS use squeezed vacuum as input, which is easier to prepare. So the squeezed vacuum, as you can see from this equation, is a coherent superposition of different even photon number states with a fixed phase relation from 0, 2 photons, 4 photons, 6 photons, and so on. So what the Gaussian boson sampling brings in on top of the past superposition in the original boson sampling is that there are also different input photon number combinations that will make the computational problem even more complicated. So for example, if we detect 4 photons in the output, it can be from a combination of input photon number 4000 or 2200 or 2020 and so on. So the output distribution is now related to a slightly different matrix function called Hafnian. And this Hafnian is also mathematically related to permanent. And it's also a computationally hard problem in the sharp P hard complexity class. So we can summarize that a dramatic difference is that while most previous multi-photon experiments were afraid of the multi-pair emission and only exploit the tip of the iceberg of the SPDC, the Gaussian boson sampling overcomes this limitation. So the overall efficiency of boson sampling can be greatly enhanced. Now let's go to the experiment part, from the idea to the experiment. So we hope to send 50 single mode squeezed state into 100 times 100 mode in a filament, and the output has 100 single photon detectors. So although the idea is clear, there's a number of important challenges that I need to overcome, including the source in the filmeters, phase locking, which I will explain in detail. So first, we need 50 single mode squeezed states, and they should all have high squeezing parameters, indistinguishability, and efficiency simultaneously. 50 is not a small number, and to simultaneously have sufficient brightness, we need a high power laser. So instead of what we frequently used, 80 megahertz, we custom design a new pulse laser with a repetition rate of 250 kilohertz, which is about a few hundred times lower in the repetition. So the peak power is much higher. And from this laser, usually, the output, the laser output is not transform limited, which will dramatically influence the photon indistinguishability. So we used a deformable nailer to compensate the high order dispersion inside the laser, so that the output spectrum is transform limited, which can be seen from the intensity and the phase data. And the laser is split into 25 paths and focus on 25 PBKDP crystals with this geometry, which are designed to have frequency correlated, as you can see from the joint spectrum. So this shows squeezing parameters and the phase of the 25 two-mode squeeze state, which is these Wegener functions. So the 25 two-mode squeeze state is equivalent to 50 single-mode squeeze state with our spatial polarization encoding. So unlike the original boson sampling, where there's no phase relation between single photons, the Gaussian boson sampling requires phase control of all the photon number states from the 25 crystals to the 100 mode in the field meter. So we develop active phase locking for each optical path. Each one consists of 20-meter optical fiber and 1-meter free space. So it's about 22 meter long. We use the pump laser, which is 775 nanometers, which because it shares the same, it's collinear with it's a collinear as PDC, so it shares the same propagation path as down-convoluted photons. We use it as a reference for locking, and inside the interferometer we use passive stabilization, and its overall drift is controlled within about 25 nanometers for a duration of 1 hour, which is sufficient for data collection. We only use a few hundred seconds for data collection. And the sampling matrix looks, as you can see, it's pretty random, as you can see from both the amplitude and the phase. So here we are at the whole setup looks like this. I know it looks a little bit scary, but we did it. Well, mostly, the students are very hardworking and very brilliant. So let me guide you through. So from the custom-made laser system to the quantum light source, each are collected into a single mode fiber, and each single mode fiber is winded around a piezo for the phase locking. And actually, the design of the geometry of the quantum light source here and the interferometer part is precisely what we actually arranged in the optical table, because we figure out that this is the most compact way to put all these components on the optical table. So after building the setup, we need to calibrate our system. For the calibration, we choose small scale and easy region. We only let in 2 pairs of squeeze state, and because the photon number is small, so we can obtain the full distribution of the 2 photon output. And we run all the different combinations, all the 23 different combinations of the input to calibrate our system. So for all the 23 different input combinations, the fidelity is on average 99%, which gives us confidence that the machine is learning properly. Then we let in all the 25 input. In the output, we get a photon number distribution because input photon is a photon number, superposition, which naturally have a distribution. So the output has the average photon number of 43, and the peak is 76. We can calculate the corresponding output hyperspace as a function. The output hyperspace grows exponentially with a function of both the photon number and the mode number. So the largest one is 10 to the power of 30, which is 14th order of magnitude larger than the previous Google experiment. So the huge hyperspace gives us a big problem because it's not possible to get the full distribution. So the 10 to the power of 30 is so huge, we can never get the full counts for each combination. And this is called the sparse region. Meaning that there's only a very small fraction of the output combination can be obtained, can obtain one event, and the most output will have 0 events. And moreover, when the output click number exceeds 40, actually the calculation of the matrix function will become too expensive or intractable for classical computers. So these 2 problems pose significant challenge in the verification of the boson sampling results. We will emphasize again that this is very this is not similar to the Shor's algorithm, because in Shor's algorithm, while the factoring is difficult, the verification is very easy. You can easily multiply two numbers together and to check. But for the GBS, which is by definition, related to the Sharpe problem, a full certification of the outcome is by definition strongly believed to intractable for classical computation. So what's our solution? So we hope to provide evidence to the quantum mechanical nature of GBS device and rule out all the possible hypotheses which are plausibly to occur in this experiment. So for our optical experiment, the two most important hypotheses are thermal states, which, if there's some excessive photon loss, there's some, bigger photon loss, then the squeeze state will be transformed into a thermal state. And also, if there's some major mode mismatch, then the photons will be distinguishable. And both of these will will reduce the quantum nature of the problem. So first, we look at the whole distribution, as shown in this figure. Clearly, there's some, and we also calculate those for thermal state and the distinguishable photons. So clearly, there's some strong deviations in the line shapes and the peak positions. And also then we calculate the 2-point correlations, which is similar to the LGBT correlations of between the photon counts. So our experiment is in a very good agreement with the theory and with strong deviations from both the thermal state and the distinguishable photons. And next we look closely into each clique number, each subspace of a specific photon clique number. So after the proposal of boson sampling, actually one of the earliest critic size to boson sampling is that the output will be indistinguishable from a random, from a uniform random outcome. So a signature of junior quantum boson sampling is that there will be constructive and destructive interference. So a boson sampling will be expected to generate samples with exponentially different occurring probabilities. So we show that up to 40 photons, you can see indeed that the intensity of the blue lines, which means the frequency of occurrence is indeed, in a good agreement with the theoretically calculated probability, which means, it cannot be a uniform sampler. And we further use a method we call the heavy output generation ratio to rule out the thermal states for up to 38 photons. And although we can only, here we can only verify for 38 photons, actually because this region we certified actually is a post-selected subspace, which effectively suffer from more photon loss than the region of high photons. So because input photon is always the same, and here is clearly, with more photon loss. So thermal meaning, the less photon loss, less unlikely, it will be thermal state. So actually we can infer that as a larger photon number regime will be validated from the thermal state hypothesis with even higher confidence. So as we write in our paper, we hope our work will inspire new theoretical efforts to calculate and verify the GBS, and we also welcome challenges from a broader community. And indeed, very soon after our publication, there was a spoof sample attack from John Martinez and Gil Clay and other colleagues. And one of the way to artificially generate a sample is from the 2-point correlations, which we later exclude by our analysis. And we hope that both the theory and the experiment will continue to develop. So finally, we estimate the classical computational cost to simulate our GBS machine. We have benchmarked GBS on as the most powerful supercomputer in China, the Sunway Taihu Light, which is the third most powerful supercomputer in the world, with a highly optimized algorithm. And the time cost scales exponentially as a function of the output photon clicks. And so for each output photon click, we calculate the corresponding time cost. You can see a line shape here, which is due to a competition between the increased computational complexity and the reduced counts at a higher number of photons. If we sum out over all the data points, we estimated that the required time cost on the Taihu light will to generate the same amount of sample in 200 seconds from the GBS will be more than 2 billion years. But of course, this is based on the current optimal method, and we hope to improve classical simulation strategies that will challenge this observation. And in fact, we ourselves are developing some new classical algorithms. And you probably have heard from or read from Scott Allison's blog that in the original manuscript we just classically verified up to 30 photons, and his review report motivated us to go up to 40 photons, which is quite costly. But on the other hand, if we look at the bright side, it means if we can find some practical applications based on GBS, then we can make a fortune. So as I said, like Bell states, like Bell tests, quantum computational advantage will not be a single shot experiment, but will require long-term computation between fast classical simulations and improved quantum device. The race is on, so we move on and improve the performance of our Jiuzhan machine. For the quantum light source, we use stimulated SPDC, which has increased the brightness 4 times with the same pump power. And for the optical network, we have also upgraded from the 100 mode to 144 modes. So such improvement will give significant enhancement, I think more than 8 orders of magnitude more. And our preliminary data have detected photon number over 100, and we are still optimizing and analyzing the data. So the natural next step is to make the interferometer tunable. So actually, there's some comments that say our GBS machine is not tunable. It's not fully tunable, but partially tunable, because the phase and amplitude of the input squeeze state can be tuned. And we will have also made the quantum light source more compact and integrated using 3D printing. And also in the future, we hope to shrink the whole system on a chip. Perhaps more exciting is to find applications that are suitable for this particular device. And the possible candidates we are considering including quantum machine learning and quantum chemistry problems, which might be mathematically mapped into the Gaussian boson sampling. So I think my time is up. So I would like to wrap up by stealing another well-known slide from John Plaskill. As he said, the frontier of physics include not only controlling very small things and very large distances, but also there's a complexity frontier where the whole community is making exciting progress in entangling increasingly more qubits for quantum computing. And we will keep on working on this frontier. So many people make important contributions to this work. Jiang Wei and I conceived the boson sampling project together about 7 years ago. And over the years, we received support from many colleagues and friends, including the quantum dot sample from Sven Hoflin in Würzburg, single photon detector from Li Xian in Shanghai, and single photon electronics from Xiao and Taihu Sunlight supercomputer from Wuxi. So real hero of this work are my students and postdocs who did the harder part of the work, and it has been a great fun to work with these brilliant minds. So finally, because the major part of the Jiuzhang work has been performed during the period of COVID-19 outbreak, so in the fight against the pandemic, we see many everyday heroes. They are hiding among us and to whom we dedicate our work to. And with that, I would like to thank you for your attention, and let me look for any questions if there's any in the chat box.
Thanks a lot, Chao-Yang, for the very comprehensive, very detailed, very nice seminar. So wonderful work, of course. We have some claps for you, as it seems to begin with, which you can see. But we don't have any questions directly in the chat. But then, of course, people can just raise hands, and we can unmute and ask. So do people have questions? Or they are just still trying to absorb everything that you said, which was a lot. Any questions, comments from the audience here? Well, while they are thinking, maybe I can just begin the question answer thing. I mean, it's more a general question. So I mean, when you did this work and the series of work that was done towards various achievements in Gaussian boson sampling. I mean, was the motivation essentially to come up with something where you can show the computational advantage and kind of make a case for the fact that it is good to have these many photons and these many channels, and you can actually solve a problem, which is the the Hafnian and so on by using this system? Was there any physical motivation that was there in your mind, like some physics-based problem, which also perhaps can be attacked using this clearly gigantic enterprise that you have created with this huge system, which I have of course physically seen? So is it essentially just about saying that, okay, here we have a problem which now we have solved, which would have been this much difficult using a classical computer? Or is there, I mean, as you began your talk by saying it's not useful, that is something I noted down. So is that something you wanted to elaborate on? Like, did you really feel that it was not useful when you were, it's more for the students really. So were you motivated by, what were you motivated by?
Yeah, it's, I think it's a very good question. So I think there are mainly two-fold of motivation. So one is that it will give us confidence of the quantum computing to the quantum community. So because eventually if we build a fault-tolerant quantum computer, it will take more, maybe like 20 years. And the founding agency, the government, or the commercial, the market will be, it's usually difficult to continuously fund to fund a field like in 40 or 50 years. If they continue to promise but cannot deliver any machine. So in this case, in this regard, it's nice to have a step-by-step near-term, intermediate-term, and long-term goal of quantum computing. So although quantum advantage, computational advantage is not as useful as the intermediate and the long-term goals, it will show the computational power which was discussed by the theoretical physicist. I think it can date back to Richard Feynman. It was widely believed, but as a physicist, we need evidence. So I think it's very nice to actually to see the quantum speed up, and more fundamentally, it's a computational analog of Bell experiments. There was this extended Church-Turing thesis, which was released in 1993. After the quantum algorithms were proposed, of course, it was widely believed it is not true, but still, we need some evidence to refute this thesis. I think there's a question from Greg.
Gregor Weiss.
He raised
Yeah.
in the chat window. Let me see.
I can read it out for the people. So so this is from Gregor Weiss. Do you see any chance to do Gaussian boson sampling of comparable size in a photonic integrated circuit anytime soon?
Yeah, it's a very good question. Actually, I have also been thinking about this question, this problem. It will be very, very nice if we can put all the currently, put our whole lab system onto a chip. So it will consist of 3 parts: the quantum light source, the circuit, and the detector. So for the quantum light source, I think the challenge is how we can simultaneously fulfill all the checklist. So to have sufficiently squeezed parameter, sufficient high brightness at this strong pumping, the crystal should behave as nicely as in the weak pumping. And also it should be frequency uncorrelated. There are some progress. I think this might be the easiest part if we want to integrate the GPS on a photonic circuit, integrate circuit. I think it's a more challenging part is the ultra low loss circuit. So because we have so the depths, for example, in our experiment we have 100 times 100 optical circuit, which means the photon need to go through many, like 100 beam splitters, and we have to control the propagation loss and the beam splitting loss to be very low. I think we can calculate if we want to. So our micro optical approach, the transformation through the interferometer itself is more than 98%. So that's, I think, will demand a lot of engineering effort. And perhaps the most difficult thing is how to integrate the single photon detectors also on chip with high efficiency. And then you also have to think about having a very high OD filters to filter out on-chip laser source, which is usually much higher. The OD typically need like 8 to 10. So you will need very extremely excellent optical filters on chip. I think that's something which does not exist already. So I think the significant challenge, I will say, the most significant one is the detector and the filters, then ultra low loss circuit, and then quantum light source. I hope I answer your question, Greg. Long time no see. And can you explain the second question? Can you please explain the extended in what sense you refute and its significance? So the extended Church-Turing thesis says that any physical realizable system can be efficiently simulated on a Turing thesis. I think it is so the Turing thesis is correct, So I think this thesis is wanted to test the computational capability, or what is the computational limit of the classical computers. And the thesis is that all the physical systems, the computational power of all the physical systems, which is obviously contradicted with Feynman's observation. The quantum states, the many-body quantum systems cannot efficiently simulate on a classical computer. This thesis is, I think, is very significant in the field of computer scientists, the complexity, computer complexity field especially. because it is about, it's like in physics, we know there's some limit that our physical law cannot surpass. For example, light cannot travel over the speed of a particle cannot travel over the speed of light, something like that. So similarly, that's what the computational scientists fairly, they think it very seriously. What is the limit of our classical computing power? Do you plan to, so the third question, actually the third question is,
From Chandrasekhar Chao-Yang.
yeah, how much of input from your work will have researchers on bosonic state quantum computing? You mentioned some tunability possible. So from my perspective, I think the boson sampling is a non-universal model of quantum computing, or meaning, it's a simplified model of linear optical quantum computing, which which you mentioned. So I think the most important message I would say is that if we cannot even perform, if we failed at perform a large scale boson sampling, then a large scale universal linear optical quantum computing is definitely not possible, because that's a much easier version of the linear optical quantum computing. So everything we developed in boson sampling will be helpful in the universal linear optical quantum computing, including the quantum light source, for example, the KLM skin, and all the skins in optical quantum computing will heavily rely on a high quality single photon source. Perhaps eventually we need 99% or even 99.9%. And also the detectors and the optical circuit. But for the universal fault tolerant quantum computing, there's some much more demanding requirements. For example, in the indistinguishability and efficiency, maybe they will all need to go above 99.9%. And also you will need a very high, fast and ultra low loss switch to have feed forward and feed backward based on your measurement result. It will need to, because the working of KM scheme relies on the measurement induced nonlinearity. So you will need a feed forward, which will have to have very high speed and a low loss. And also for the detect, eventually maybe we also need like 99 point something percent. So everything we develop is useful, but I think it's still far away from what we will need eventually. It's a step. It's probably not a leap, but it's a step.
So Chao-Yang, I just want to read out the questions because it's getting recorded. So the chat window doesn't get recorded. So just for, you can read it as well, but let me read it out aloud also for the recording purpose. So the next question is for Sergey Sluzarenko. Thank you for the talk. Do you plan to move to quantum dot sources for the future demonstrations, or the focus is now on SPDC only?
So as I said, the single photon source is a very useful, or it's a very useful resource. So we will try to optimize the quantum dot single photon source efficiency and also performance anyway. And we do plan to also demonstrate the original Scholar Allison proposal of boson sampling up to 30 or even more photons. But also I think the single photons will find other applications. Last year we demonstrate intensity squeezing using quantum dot single photon source, which means you can have a higher precision measurement of a certain quantity. And also, the quantum dot single photon source will be useful for quantum network and for quantum communications. Possibly, in the future we can equip it in the next satellite, or next mission satellite, to further enhance the efficiency of quantum communications. And also we can think about building solid state quantum networks based on the single photon source.
Okay, so the next question is from Anindya Sinha. I have a naive question. How did you benchmark your machine for accuracy? I understood that your result would be impossible to reproduce classically. Using a smaller number of channels, would you be able to perform something that can be done on a classical computer? If not, what is the guarantee that your result is reliable? Sorry, this is a night question.
So yeah, actually, it's a very good question. As I said, because for larger scale boson sampling, it's by default that it cannot be completely verified because it's sharper P problem, meaning you calculate either way is difficult, not just a one-way difficult. So what we do is that at a small scale, we fully categorize our system. As I said, the fidelity is 99%. And at a larger scale where when it's impossible to fully calculate, then we use validation methods to rule out the most plausible hypothesis, the thermal state and the distinguishable photons. Actually, our second experiment, which we are running just now, we will deliberately perform a small scale experiment, which the photon number will be focused around 10 to 20. And at a zero regime, maybe everyone can use their laptop to test and to play along and to validate and to do all different things. And we will share that on on public so that everyone can download and can play along with. Because if we share just the 50 or 76 photon data, only if you are very rich and you can rent a supercomputer, then you cannot you cannot play with it.
Yeah, since you talked about the rich, if I may ask, what is the ballpark cost of this experiment?
What is overall cost?
Yeah, in the ballpark, is it
Oh,
100
okay.
thousand? What, I don't know. Yeah.
So for we in Chinese yuan,
Sure.
Chinese yuan is about 6 Chinese yuan is about $1. So the budget of our experiment, so the Jiuzhang experiment, we cost about 30 million Chinese yuan. I think this is about $5 million, including the most expensive part is a single nanowire
Detector.
superconducting detectors. We got
Yes.
many.
Yes, yes, yes. I was seeing, the number there is huge, right? The number of detectors you have.
And our colleagues in the supercomputer, so they covered all the electricity cost and everything. So
Okay.
that is not included.
Wow.
Yeah.
So
But
overall, it even goes up. Yeah.
yeah, roughly I think it's about $5 million. Excluding the lab space, something like
Sure.
that.
And
Electricity, water.
so many
Yeah.
people. Yeah, yeah, yeah. But you were just
Oh yeah,
talking
yeah.
from the,
Also,
yeah,
also excluding our salary and
yeah.
the students' salary.
Yes, yes, yes. So that is a detail. Yeah, that's great. So, right. So do we have any further questions or comments? Not in the chat window, but does anyone want to say something? Otherwise, yeah, seems we are doing okay for now. So I think we've had a lot of questions, Chao-Yang. So thanks a lot once again for this excellent seminar. So it was a great start to our series as well. And so on that note, thank you very much, and see you all for the next RRI Quantum Science and Technology webinar. See you.
Thank
Bye.
you.
Bye,
Have a
everyone.
good day.
Yeah.
Bye bye.